So welcome to the Zebra walkthrough. I'm just going to be going over some of the key high-level parts of Zebra's code base today, starting with the cargo.toml of the Zebra D crate, which is the main entry point into this cargo workspace. So by default, it runs Zebra D, which is here. It boots the application, which is here. And this is just an Abacissa application. There's nothing very interesting here, except for the commands. These are the main commands that you can use with Zebra by running Zebra D start, generate, copy state, etc. Inside them, you'll see that they have their own options. Today, I think we're going to be focusing on the start command because that's what everyone usually, that's the main thing that we use. So let's start with the start command. Here we see that if it's regtest, it does some special stuff. It updates the config to enable the mempool starting at height 0. But in general, it reads in a list of checkpoints, initializes the state service with a database and a non-finalized state. I'll get into that a lot more later. And it uses these buffers for most of the tower services. So there will be one service and there will be a buffer that queues up requests so that the buffer can be shared across threads without having to duplicate the state of any of these services. Then we have the inbound service. This is what, when network requests come to Zebra, they go to the inbound service and it answers them. We have the peer set, which manages all of the external peer connections that Zebra has, essentially like the inbound service, but the opposite. Then there is the block verifier router, the transaction verifier, and some consensus task handles. We will see the consensus task handles in a minute, but the block verifier router, exactly what it sounds like. It just does semantic verification of blocks and then passes them over to the state service for contextual validation. Transaction verifier does semantic validation of transactions. Then we have the syncer. The syncer uses the peer set and the block verifier router to sync blocks from the network. The mempool. This also uses the inbound service and the peer set. The inbound service to look up transactions. The peer set, it uses the peer set to gossip transactions and advertise them to others. It uses the state to validate them, mostly getting the tip height. It uses the sync status to decide when to be enabled, and the chain tip change to manage what transactions are in the mempool, kick some of them out. Then we have this weird little inbound setup data thing. This is because sometimes when you want to initialize a service and then pass it to another service, but also keep a copy of the first service in the second service, so they're both calling each other, you have to do this little thing with a channel. Then we have the RPC server. This is not really used yet, except for the chain tip change RPC method, but there's also an indexer RPC server. This is with tonic and gRPC, whereas this one is JSON RPC. Then we have the block gossip task handle. This just listens for chain tip changes from the state and gossips them if the sync status is close to the tip. We have the mempool queue checker task handle. We will see why this is important in a minute, but essentially, because the tower services are only polled so often, we need to keep polling it every so often, like on a regular interval, to make sure that it's always up to date. This is related to the state service. It's not very important. It just deletes older versions of the database. This is for the progress bars, for the experimental progress bar feature, the end of support halt, the mempool crawler, and the syncer task handle just uses the chain sync component that we saw initialized above to actually start syncing blocks from the network. The miner task, enabled when the internal miner feature is selected, is going to, at least on regtest currently and on testnet, if you're on a certain branch that is using the version of the Equihash that has the chomp solver, this can mine blocks on testnet. Otherwise, it can still be used to mine blocks on regtest where proof of work is disabled for Zebra, but it will not work on testnet unless you are on that particular branch, at least for now. And it definitely won't work on mainnet. And then here, this is just managing how things are shut down. So let's start with the order that these are initialized. So the state services first. Well, let's actually go for it. So Tokyo does not like long IO in its green threads, so it has the spawn blocking. And we initialized the RocksDB instance in the spawn blocking because we don't want to cause any strange behavior with Tokyo. This is how a state service is created. It first creates the finalized state, non-finalized state. The non-finalized state is the last 100 blocks in the chain before the max reorg height. It can hold up to 100 chains and chain forks at the same time. But once they reach the depth of 100, then they're finalized, and those cannot be rolled back automatically. The only way to roll those back is to use copy state, just delete the entire old state and start with the new one.
Can you increase the font size? Paku asked, but it
Absolutely.
would also be useful for me. That's perfect. Thank you.
Thank you for letting me know. And then within the state service, we have a deeper state service, which is what the channels are for. So the non-finalized and finalized block write channels are going to be passed to the write task. Which is here, and we'll see what that's doing in a moment. But first, let's see how blocks are sent to those channels. Nothing much very interesting happening here. So let's now look at the implementation of service. So this is the pull ready method for the state service. It really just manages this prune interval and checks if the read service, which is used by the state service, is also ready, because many of the requests are just routed over to the read state service. The prune is for appending UTXO's struct, which is a set of broadcast or watch channels where the transaction verifier can await a UTXO that is not yet in the state. And if within a certain timeout, I think it's 65 seconds, or within a certain timeout, if the block becomes available and the output becomes available, it can still verify that transaction. Otherwise, it'll have to resync the block. And here we're just pruning old channels that are outdated from longer than 65 seconds ago. This is the main request that the state service is using, commit semantically verified and commit checkpoint verified. Let's do checkpoint verified because it's easier first. It just checks against the ordered pending UTXOs. So if there are any outputs that other requests are waiting on, then it passes those in, and then it queues and commits it to the right block task. Now the slightly more complicated.
Hang on,
yes?
you're going too fast. That seems like a thing to go into more detail about. So is there a particular order in which sort of outputs need to be verified?
Do you mean the pending UTXOs?
Yeah, so they're the UTXOs that haven't been verified yet. Is that right?
No.
Okay.
Yes, no. I'll show you where it's used.
Okay. Thanks.
This is the await UTXO request. So the transaction verifier here will check for when it's verifying transactions from a block. It will first check if a UTXO is available in the state at all. And if it's not, then it will check, then it will queue up an await UTXO request, which adds a channel to this structure. And then once, so if it's there already, it'll respond, but otherwise it'll just pass back that channel. And it's, I think it's a one shot or a watch channel, but anyways, it checks.
So like a future. Okay.
Yeah, it's a future. And then it checks against the order so that if there's already an out point queued in the pending UTXO struct, then if the output for that out point is being added, it will, before you can commit and block to the state, say, yeah, we think we have this output.
Your sound is garbling a little bit, Arya.
A little choppy.
I
Is this
think other
better?
people are. We'll see.
Okay. But
no, it's the same.
It's the same. But no.
Yeah.
Is this a little better?
Yes, it sounds like
could
it might
be
have been bad batteries or something like that, and
I think it's magnetic interference.
Oh no, this is worse.
Yeah. Oh, this is worse.
About the same, I think. I think it's probably the same cause, whatever it is.
Yeah.
I mean, it's usually understandable. It's just occasionally a sentence will break down completely.
Got it. Okay. So please ask me to repeat something if it's not clearly being transmitted.
Will do. So repeat what you said just then.
Got it. So in the await UTXOs area, it will queue up an out point that the transaction verifier is waiting on. And then when the block is being queued for to be committed, if it has that output, it will pass that output to the channel. It just responds.
Got it.
And then it queues and commits to the non-finalized state here, just like it was queued and committed to the finalized state. In both cases, it will wait until the previous block, the block with the previous block hash is available before it sends them to the right block task, because these can be sent to the state service in any order. There are a bunch of rules that have to be validated besides, actually not really for the finalized one, but for the non-finalized state, there are a few other rules that have to be validated first. And it also uses a response channel to wait until the block has been committed to the state before responding to the request. So we see that here, it's actually just passing back, it's waiting on the response before it returns a response to this call. And then here, we queue the blocks in a set of queued blocks so that in case they are being received out of order, we can wait until the previous block is available before sending it to the right block task. We add it to the set of sent hashes because we want to check that we can fork the chain at that block hash because the previous block hash is available before we send it to the right block task. And then the interesting part here is just send ready non-finalized queued. So once
I didn't quite catch. So that can fork thing, I didn't understand that.
So it just checks that we've already sent the hash, like the block hash, that is the previous block hash of the current block, before saying that we can send the new block to the right block task. So unless we have the previous block somewhere in the state, we don't send the block to the right block task.
I see.
Okay, cool.
Oh, so you're not writing blocks, that's what. Correct.
And then send ready non-finalized queued. It's just going to take the parent, pop it, and then go down as many children as it can and send them all over to the block write task. This is fairly straightforward. And then at this point, I think what we want to look at next is the write block task. So
before you do,
yes,
I think so. You've got a very large video window there, and I think maybe the resolution is increasing your bandwidth, and that's affecting the sound. That's my theory. So if you were to reduce the number of pixels in the window.
okay, I'm not sure how to.
Are you sharing the whole screen or just one window?
The whole screen, but I don't think it'll help. I think it is magnetic interference because I have this problem with other Bluetooth devices as well.
Oh, okay. All right.
Sorry about that. So yes, the finalized blocks are going to be written first, and we know that there aren't going to be any non-finalized writes, at least not directly, until we are finished with the finalized blocks. So it's going to just keep receiving finalized blocks and then committing them directly. And when we commit a finalized block, we don't check really anything at all. Okay, that's not true. We do check a few things, but we check very, very few things because we know that they're coming from checkpoints. So this loop is relatively simple. We send the result back.
I'm confused about something. So I thought that finalized meant at least 100 blocks back rather than checkpointed.
Yeah. It does. It absolutely does.
So I'm maybe being confused by what Zcash does for checkpoints. So in Zcash, checkpoints are only manual, and occasionally you will hard code a checkpoint into the code, but we don't count say everything 100 blocks back as checkpointed.
Oh, Zebra doesn't either. I'll explain
Right.
in just a moment. So
okay,
for blocks to be committed via this channel, they have to go through commit checkpoint verified block, like these requests. These requests only come from the checkpoint verifier. So after we're done with the checkpoints, there aren't going to be any more of these calls. There are going to be non-finalized calls, the commits and semantically verified block, but these will go to the non-finalized write block sender, and they won't be received in this loop at all. They'll be received here. They'll be received here. They'll be added to the non-finalized state first, and after we add a block to the non-finalized state, we check if the length of the non-finalized state's best chain is greater than the max block reorg height. And I'm just realizing this means that it could actually be a little longer than the max block reorg height, because a sidechain with less work could have more than 100 blocks. But for the most part, after 100 blocks, then it will try to finalize the block, which just converts it into it removes it from the non-finalized state, converts it to a contextually validated block, and it commits the finalized direct. Still doesn't do very much validation, but that's okay because it's validated when it is being added to the non-finalized state. Daira-Emma?
Do I still have my hand up?
Okay, never mind.
Ago.
So
I think I've got it, but so you're doing the validation when you add to the chain tip effectively the non-finalized state. but you count everything before the last checkpoint. That goes through a different path, and so you do
Exactly.
fewer checks on that. Okay.
It actually goes through an entirely different channel. And there are practically, I mean, there are a few checks, but there are very few checks. It's not the full set of validation happening there. The same process happens when we're finalizing blocks after it reaches the max block reorg height, but that's okay because they're validated before they're added to the non-finalized state where they're coming from.
And the thing that you said about
how...
the thing that you said about the possibly being more than 100 blocks, that only happens on a reorg, right?
No, that would happen if so the best chain can only be 100 blocks, but a side chain could have less work than the best chain and be longer than 100 blocks. Does that make sense? Because the best chain is always the one that has the most work.
Oh, I see what you mean.
So the best chain can only be 100 blocks, but if a side chain with much less work has an extra 3 or 4 blocks, in some rare instances, a side chain, So then we check the initial contextual validity. We check that this creates an iterator of blocks that goes backwards via the previous block hash. And then we check the median, like we check the block time. We validate a few rules. We check that there are no duplicates, nullifiers. And then we do a whole bunch of other validation in either commit new chain or commit block. Commit new chain just goes through commit block. So let's just look at commit block for now. It gets the parent chain, it modifies it with an attempt to validate and commit, and then it inserts it back into the set. And this is a B tree map, so it will reorder itself when you're adding anything in. Validate and commit checks.
I think Nate had a question.
Yes, Nate?
Oh yeah, I was curious about the relationship between the these different states and validation channels and the write service. So what gets written in this pipeline?
Okay. So back to a little bit of an overview. The block verifier, like the semantic block verifier, the one that actually checks rules, goes through the commit semantically verified request. The checkpoint verifier goes through this one. For commit semantically verified blocks, it'll go through the non-finalized channel, and for this one, it goes through the finalized channel. So the finalized channel, we assume that all of these are they're checkpointed, so we don't do very many validation rules. For the non-finalized channel, it always gets committed to the non-finalized state first through validate and commit non-finalize. And then if the best chain is longer than 100 blocks, it will finalize that and commit that directly to the finalized state. Does that answer the question?
Is there a diagram of this anywhere?
Yeah, is there like a flow chart? That would help me a lot.
There really should be, but I don't think there's one right now. I can create one after this.
So is the finalized, if something is sent to the finalized state verifier, then once it is verified, it gets written? Is that when writing happens?
So if it's a checkpoint verified block, it gets committed to the finalized state directly. It doesn't go through the non-finalized state at all. If it's a semantically verified block, then it's not written to disk, but it is written to memory. It's validated and written to memory. Does that answer the question?
When do blocks get written to disk? And what is that pathway?
So whenever we commit a block to the non-finalized state successfully, we will check the new length of the best chain in the finalized state, which has likely just been updated. And if it's too long, if
You
it's
mean
more
in
than
the
100.
in the non-finalized state?
So if we commit blocks that are semantically verified to the non-finalized state first, and then if that's successful, if it's not successful, we just continue on to the next block. But if that's successful, we update the latest chain channels, which is the chain tip change, the latest chain tip, and the non-finalized state center. And then we check that the non-finalized state's best chain is less than or equal to the 99 blocks. So if it's at 100 blocks, then it will finalize one of the blocks and add that to the finalized state directly.
And does the finalized state get written?
Yes.
Like whenever we're adding to finalized state, that's when writing occurs?
Yes. Yes.
Okay.
So commit finalized direct will attempt to write it to disk, to RocksDB.
Okay. Yeah, thanks. That was my question.
Yeah, does that occur? So is that durable? Does RocksDB give you a guarantee that that's definitely written before it returns?
Yes.
Okay.
We can take a look at that in a moment. But yes. So for non-finalized blocks or any blocks that are not checkpointed, it will check the initial contextual validity, which checks for the median time span, that there are no duplicate nullifiers, and then it will go on to try and commit the block to the non-finalized state through this method. Validate and commit will check that the transparent spend, including the transparent spend chain order, is correct. So there are no outputs being spent before they're created. It checks the Coinbase spend restriction and the remaining transaction value. It checks that the final that the anchors refer to the final tree state. So these are checks that don't happen in the transaction verifier because it's just not very efficient to do that. And then it creates the contextually verified block with the spent UTXOs. This is information that we're going to need later when we're writing it to the to RocksDB. It does some more validation steps here. These are the ones that can be done in parallel and are being done in parallel because they were a little bit slow.
So the things that you said weren't being checked for individual transactions. Are they so semantically transaction checks in the specification, but they're being deferred, make them more efficient, or are they
deferred? Because the transaction verifier doesn't have, I mean, it does have access to the state, but it doesn't have access to the, there are blocks that could be validated in parallel elsewhere in Zebra, like in the block verifier or other transactions that are going through the transaction verifier. So not all their outputs are immediately available in the state, and not, well, like they haven't updated the tree states. So we wait until the previous block has been committed to the state before validating these rules. All the contextual checks.
I see.
Yeah.
Yeah, because you can do some of the checks before you have the previous block state. Okay.
Yes. Yeah. Including, and some of them are best effort, like the 08 UTXO that I just showed you. The purpose is not to validate with complete certainty that all those outputs are available. Some of those outputs may not actually be committed to the state in the end. It just says the state is aware of these outputs. They are candidates. They may be committed. So try validating this transaction semantically. And then if it could pass contextual validation later. If it's not valid later, then it'll be rejected here.
Oh, I see.
So yeah, it just creates the contextually validated block. It does a few more things in parallel, like checking the sprout anchors because this is disk IO. And then it just commits it to the non-finalized state. And it pushes the new block into the new chain, and I believe it returns it returns the updated modified chain, and then it gets returned from here, and the chain is inserted back into the set of chains, which is a tree map. So it'll be sorted, and if it's the new best chain, then it will go to index 1, and later when we are updating the latest chain channels, it will be clear to everyone that is receiving these, at least in the chain tip change struct, what the last tip hash was. So if the previous block hash of the new block, the new chain tip block, doesn't match the last hash, we know that there was a chain reorg.
So this is done in quite a different way than Zcash-D. Zcash-D will basically just keep track of the best chain, and then it does a stateful. It rolls back to the common ancestor, and then rolls forward to the new block if there's a reorg. So having had experience of doing it the way that Zebra does, keeping track of multiple chains, what would you say the trade-offs are there? Because I know there was some discussion about this recently, and I can't remember what the conclusion was.
So I would say that keeping track of multiple chains is unambiguously easier to work with, but what makes it more difficult to work with is because these are all happening concurrently, a lot of the other services, they don't have direct access to the state, and they don't have direct notifications of all of the blocks that change. So in the mempool especially, what we do is we just revalidate every transaction when there's when the tip grows, and we throw them all out and try to revalidate them when the state is reset. It's a little inconvenient in some places, but the performance gain is significant. So I think it's essentially a trade-off between performance and ease of development on the concurrency side. For keeping track of a bunch of side chains, that makes it a little easier to deal with the concurrency, I think.
So just to clarify, it's kind of a hybrid model where you're keeping track of multiple mined chains, but for the mempool, you will only have validated those transactions against the best chain, and so if that changes, then you have to revalidate.
Yes.
Does that apply even when you're just extending the best chain?
Yes.
Or okay, is that not inefficient when you have a lot of transactions in the mempool?
It is inefficient, but it only happens once every 75. It's only expected to happen once every 75 seconds, and verifying the transactions is relatively quick, so it's okay for now. We could change that in the future. It could query the state to see if it's still valid. But
yeah, I can't remember. I can't remember how Zcash-D ensures that the mempool is still all valid. I think it does it on a really ad hoc basis with just particular consensus rules can fail when the state is updated.
Yeah, that's the optimized way to do it.
That's probably not a very principled way to do it.
It is for performance, that's better, but less performance because everything is happening in parallel. So in general, it's usually just quick enough already. There are a lot of places in Zebra actually that the performance could be improved relatively easily, but it's just already good.
Do those tend to have tickets?
No, a lot of them
issues?
don't have. A lot of them don't have tickets.
Okay.
Except for the biggest ones, like for example, automatically verifying transactions that have already been added to the mempool. That has a ticket and a PR open because that's a really big one. But most of these only really get tickets if we notice that it becomes an issue, and usually it's not really much of an issue.
Okay, thanks.
Okay, and then so it also sends a version, like it clones the non-finalized state. Don't worry, this clone is actually just an arc.
Sorry, before we go on, could I interrupt with a question about the mempool interaction with the rest of the state, the validation state?
Mm-hmm.
So my question was if there's a transaction T that goes into the mempool, and then later it's validated in a non-finalized block, and then there's a rollback and it appears in a new block. What does that look like in terms of the mempool service versus the non-finalized validation state? Does that make sense? That question.
So if a transaction in the mempool is mined onto the best chain, and then it's rolled, like there's a chain reorg, so that would be a chain tip. It would be a reset tip action, and it would attempt to re-verify all the transactions except if it's already been mined onto the best chain. The mempool removes any mined IDs from itself when the tick grows. It doesn't even try to revalidate them because it knows that it's already been mined onto the chain. So it would be gone. It would have to be gossiped again from a peer node, or the mempool would have to crawl and ask for that transaction. It would have to be re-downloaded.
Okay, thanks.
Oh, I see. I didn't realize that. Okay. So if a transaction is unmined in Zebra, then the only way for it to get back into the mempool is from another node.
If it was mined onto the best chain and then there was a chain reorg, yes, yeah.
Okay, interesting.
And then so this is the core part of a large we did about 2 years ago, where there was an issue with committing blocks because it would receive blocks out of order, and up to like 400 of them. And the state service was blocked until all of those blocks could be committed. But the right block channel was added, and this non-finalized state watch channel was added, where it's essentially like an eventually consistent data structure. It will send the latest non-finalized state to the sender, and that's what the state service uses to respond to all the read state requests, or yeah, all of the read state requests. And I think that's about it for the right block channel. There are a couple other details, like how these errors are handled, but that's not terribly interesting. Elsewhere in the state service, we also have check block proposal, which I think is interesting. So I will show how this works. So this is used by the getBlock template method in proposal mode. What it does is just clones the non-finalized state, and it attempts to, it does commit a block to the non-finalized state, and then it drops the clone of the non-finalized state. And that's how we check that a block can be can be submitted and will be accepted before the solution has been mined. The rest of these are really just used largely by RPC methods, some of them by the transaction verifier, for example, check final anchors. That's done for blocks in the contextual validation step, but for mempool transactions, we know that we're probably at the chain tip, so it's done by a state service query, and it's done in parallel. Some of these are used to respond to network requests. Not a lot more interesting here. So going back to the start command, the next service here is the inbound service. The inbound service has a request for all of the Zcash network protocol requests that are defined and that are specified. It also has a copy of the state that it uses to respond to these. It manages the inventory responses. Not a whole lot interesting here either, but this is how Zebra responds to network requests. The block verifier and the transaction verifier are much more often changed, and this is something that Shielded Labs is likely going to have to change for their proof of stake or their hybrid proof of stake and proof of work implementation. So the router is, this is the init function. I'm going to skip to the router. Where is the router? Oh, it's right here. Okay. So all this does is check if the max checkpoint height, and this is red when Zebra starts up from the list of checkpoints, if the height of the block is below or at the checkpoint height, and if it is below, then it'll go through the checkpoint verifier, and if it's above, it'll go through the block verifier. Also, if it's a proposal, it'll go. It will fail if it's below the max checkpoint height. So the checkpoint verifier, just starting with what's a little bit simpler, has its own list of queued blocks.
A question before you do that. So for checkpoints, do you only count the node as being past the checkpoint when it's the TIF is 100 blocks past, so that it's the finalized block is past the checkpoint?
These are actually, so it depends on the height of the block, and if the block height is just 1 over the max checkpoint height, it'll be considered a semantic, like it's not a checkpointed block. So it'll go through the regular block verifier and check against all the validation rules. But if it is below the checkpoint height, it will be added to a queue of blocks, and it will keep doing that until it reaches the block hash of something that actually of a checkpoint, and then it'll check all the previous hashes and it will send those all off to the state services in this function here. So this is the target checkpoint height and the expected hash. It checks those, and then it goes through the range of heights, trains them all, and sends them off to the state service.
So do you have to have all of the headers up to the checkpoint before you will consider the corresponding blocks to be before the checkpoint? So Zcash this is actually different at the moment between Bitcoin Core and Zcash, but we get headers and blocks concurrently, and so you can be in a situation where a block is before the a checkpoint that you haven't got to yet, but you don't know that it's on that chain. And so you can't you can't skip any checks. Is that also the case for Zebra?
No. So what
Sorry,
Zebra does,
I haven't explained that very well.
I think I understand though. So what Zebra does there is if it is below the checkpoint height, it will at least queue it. And then we know that there's only one list of checkpointed blocks. So once it gets to the height where it does see a block hash that it recognizes as being checkpointed, it will clear any other block hashes. It'll clear any other blocks that are not in that chain because the previous block hashes, are not that block hash.
I see. Got it. Yeah, makes sense.
All
right. So when you're syncing, you don't know which is the correct chain because you haven't got to that hash yet. And so you basically have to handle every block you receive. Is that right?
Yeah.
Okay.
And this isn't a denial of service issue because in QBlock, one of the only checks that happens here is that the difficulty is valid.
Yeah, that makes sense.
So on to the block verifier. Where is the block verifier? That's here. So the block verifier is actually quite simple. It does validate a lot more rules than the checkpoint verifier, but it's not terribly complicated. It will first check that the state doesn't already have the block. And then if it doesn't already have the block, it will check that it's not above the max height. The proof of work is one of the first checks, again, because of denial of service issues. If there is a peer that is sending a lot of these blocks over, we want to reject them as quickly as possible because there's a limited amount of space on the queue. I think it's about 400. I think it's about 400 for 800, 1200 blocks. There's a limit on that. So we check the proof of work is valid first, and then we will check the transaction rules that require the entire block, like the Merkle root validity. We check that the time is valid. We check that the coin base is first. Subsidy is valid. And then we will pass all of these transactions over to the transaction verifier. We'll take a look at that in just a moment. But that will also give us the miner fees. So here we will add up all of the miner fees and check that the miner fees are valid as well. And then we will prepare a semantically verified block with all of this information, particularly the hash, because we don't want to do that again in the state. It's a slightly expensive operation. Better do it just once. If it's a proposal, we will just check the read state service. Well, it gets routed through the state service to the read state service, but we will just check that it's a valid proposal and return that information. But otherwise, we'll commit it as a semantically verified block, send it over to the state so that it can be queued. And once its previous block hash is available, all the way down to the last block that is in the state already, it'll pass all of those off to the right block task to be validated. Are there any questions about this before we go into the transaction verifier? Okay. So the transaction verifier does all the quick checks first, again, because of denial of service issues.
Oh, sorry, I had a question, but I was
yes.
I was muted. So after you've verified an Equihash solution, the Equihash solutions are quite large, so do you remove that from memory?
No, we don't remove it from memory because it's going to be stored in the state on disk, so that we can send those blocks over to peers. It is quite large, though.
Okay.
By far the largest part of the header. Still not as bad as the transactions for a lot of, especially during the spam period. The transactions were much worse. I think this is only about 1,300 bytes.
Yes,
which is a lot.
So yeah, Zcash will also store it on disk, but Zcash has all of the headers in memory except for this optimization. Does Zebra also have all of the headers in memory?
No. All of the headers that are in the finalized state will not be in memory, if that was the question.
Yeah. Okay. Yeah. I don't know why Zcash does it that way. It's kind of silly. But yeah,
Ooh,
that's good.
Yeah, I can imagine the headers are going to be like the solutions are going to be very, very expensive. That makes sense why you don't keep those in memory.
Yeah.
But for these solutions that we keep in memory, at most, I think it's maybe 1,200 blocks, plus 100 blocks times the number of chains there are, which is a maximum of 100, which could be very large as well. That could be around 20 gigabytes, I think. But in practice, there usually are not 100 side chains that are all 100 blocks long. So in practice, it's usually okay.
So if you limit the number of sidechains to 100, could there be a denial of service? I probably shouldn't be talking about possible denial of service on a public call, but could there be a denial of service for memory usage just by, well, I guess it would be a really expensive attack because you'd have to mine that many blocks at the current difficulty level.
Exactly. It would be a preposterously expensive attack, and the worst case scenario there is Zebra will just need about 20 gigabytes of memory, which is a lot, but there are probably at least a few nodes that have access to sufficient memory resources to keep the network alive. And because the attack is so expensive, it's probably going to be very rare if it ever happens at all, at least on my net.
So you've also got to consider the case where the difficulty is low for the start of the chain, but I guess that we already covered that when you were talking about denial of service on syncing.
At the start of the chain, yes, those are handled by the checkpoint verifier, and those blocks are dropped if about 400 blocks later if they're not valid. And those won't take, so the limit there is actually 1,200. It's not going to be 10,000 because there is no non-finalized state yet. All those blocks are going to be coming directly to the disk. So that actually is even less of a denial of service issue.
Okay, thanks.
So here we do the quick checks first, and if the transaction is in the mempool and it's a Coinbase, that something has gone horribly wrong. But otherwise, we just check that a couple other rules for the Coinbase are still valid, like the expiry height, the spend restriction, which I think happens a little further down, but the spend restriction, that it has a valid expiry height. And if it's not a Coinbase, then there are slightly different rules to check at the beginning. Here we do the join split check for Sprout transactions. This doesn't actually happen very often anymore because not a lot of people are creating G4 transactions with join splits, but it's there. We check for spend conflict within the transaction. So if a transaction spends the same transparent output or transparent out point twice, or if it reveals the same nullifier multiple times, then it'll return an error here. Otherwise, it will happen in the contextual validation check in here. We check that the lock time is okay, that for mempool transactions, we also check that the median time passed is okay, the lock time is passed. again, for mempool transactions here, we check that the anchors and revealed nullifiers are okay with the state because we expect that the chain is growing very slowly. And if it does grow while a transaction from the mempool is being re-verified, the tip height is saved, like the tip height that the transaction verification request was sent with. It is going to be checked again when it's finished verifying it and the mempool is doing a few final checks before adding it to its verified set. So we check the lock time. We check the state for the SMET UTXOs that the transaction is taking as inputs. For blocks, we also await the UTXOs, but for mempool transactions, we just check if it's already in the state or not. If it's not in the state, then there's no way that that transaction is going to be inserted into the verified set anyways, because the tip height would have to change before that UTXO becomes available, which would cause the mempool to re-verify it anyway. And then we check the maturity height for mempool transactions. We create a cached FFI transaction, which is checked by a Zcash script. This is just the transparent checks. So we check that the script is okay. And then here we check that the semantic information about the shielded transactions is valid. So we don't check the anchors or for duplicate nullifiers, but we do check that the signatures and proofs are all good. We get the Zcash here as well. This also goes through Zcash primitives. So it'll convert the transaction to a Zcash primitives transaction first and use the method from Libra Zcash to the Zcash.
So the contextual checks are anchors, nullifiers, yes. Expiry height, double spent or non-existent inputs. Is that everything?
Yes, that's everything, and I believe, yeah, it includes the expiry height as well. Like the contextual
and anchor validity, yeah. Did I say anchor validity?
You did. It's anchor validity, duplicate nullifiers, and expiry height. Those are the three that have to happen during contextual validation.
Yeah, because the transparency inputs are handled separately.
Exactly. And I think we sort of cheated with the transparent inputs because the outpoints are going to refer exactly to the outputs that the transaction verifier is interested in, but we can't do that by design. So it's not possible to do those in parallel, unfortunately.
It's kind of an unfortunate design. Anyway, of Bitcoin Core, I mean, or Bitcoin in general.
I wonder if we could do it better, but anyways,
there's probably like a lazy topological sort type algorithm that could be used there.
Okay, I would be interested in discussing that further if anyone has any ideas to handle checking the anchors and, well, I don't think we can check duplicate nullifiers, but at least handle checking the anchors in parallel, even some of the time, so that the state service can sometimes skip doing that during contextual validation. I think would be useful.
Oh, for nullifiers, you can do the thing that I mentioned in my Amsterdam scaling talk, which is sharding the nullifier space, because sort of checking for duplicate nullifiers overall is equivalent to checking for duplicates in partitions of the space.
That's a good idea. That's something we should do, especially because the finalized state is where those reads are expensive. In the non-finalized state, where all the new blocks that are remaining, or most of them are probably going to be, that's very cheap. So most of the time, I think that's going to be a good optimization that we should do. Thank you for that idea. So I was showing some people yesterday that this is just one line. this is the method.
Your sound dropped out.
Oh, I was mentioning to some people that this is just one line yesterday. So whether the transaction version is valid is checked in this method, and there's another one for V5 transactions that does basically the same thing. And then we verify Sprout and shielded data here. I'm going to look at the verify version 5 transactions first because, well, we can look at Sprout first. So this doesn't actually do much. It sends it off to another verifier, the join split verifier. And this will attempt to do, oh, actually this one doesn't do batch processing. Okay, so this one will just verify the proof on things individually. And then
that's interesting. You should be able to, because it's still got 16, you should be able to batch across different circuits. In fact, that's taken into account in Appendix B of the protocol spec, how to do that.
It's possible it just wasn't implemented because we don't see these very often.
Yeah,
but denial of service.
That's
I did.
Fair point.
It's annoying because the denial of service attack surface is always all of the protocol, even the bits that aren't really being used.
That's a fair point.
That's a good soundbite for motivating, deprecating old protocol pieces.
Yeah, I've been saying so for years.
Yeah, hopefully we can get rid of V4 for NU7, but in the other verifiers
I'm just writing the zip to do that now.
Yes, thank you, Daira-Emma. So in the other verifiers for sapling and orchard, we have this tower fallback crate. It's its own crate, and it doesn't really have to be used specifically with Zebra, although some dependencies are a little specific to Zebra. And it uses the batch verifier first, and it falls back on verifying single spawning, where if one of the items in the batch fails, the entire batch will fail, so all of them will have to be verified individually. And then let's take a quick look at V5 as well. Same thing, it just also adds verify orchard shielded data, and that includes the Halo 2 verifier.
Question. Sorry, yes. A question about that batching. Is that only for transactions that are grouped together in a block, or does that occur on transactions from the mempool?
Actually, it will batch transactions. It will batch verification for transaction signatures across blocks. So we could have 400 blocks with a very large number of transactions, and it could try verifying all of their proofs at once. In practice, I think there is a limit because the batch verifier has a max items in batch. And that for Halo 2 is just 2. We should take a look at increasing that.
Yeah, that seems quite small.
Very low, especially considering the effort we can retain.
Well, is it because I mean, each individual verification uses all of the cores anyway?
No. So if we look at the batch verifiers, it looks like, where is the batch verifiers? Okay.
No, I mean internally in Halo 2 proofs.
Oh, that I'm not sure about. But
I'd have to check. I'll check that now.
Okay. Let us know. Okay, and then
your audio is completely broken up at this point.
Got it.
Yeah.
It depends on how I'm sitting. So we see that these are all returning futures, and these futures are all added to the async checks. And then these async checks are a futures unordered below. I think let's look at the definition. And it's just a new type around this. So all of these will execute in parallel. And then once those are all done, let's just go back. So once all of these async checks have been pushed, and once all of them have returned a value, then if it's an error, it'll return that. Otherwise, it'll just get the value balance, the minor fee, and then it'll respond to the request. It goes back to the block verifier, which then uses the minor fees to check that the minor fees are valid. And then it passes it off to the state service. And that's the transaction verifier and the block verifier and the checkpoint verifier and the state service. And some of these script verifiers and proof verifiers. A lot of verifiers. So next is the chain sync component. This part is not terribly interesting. It's just initializing a new one. The only thing that's interesting here is the downloads component. So when transactions or when blocks are go through this, we'll see that in a second. The interesting part here is the sync method, this, which is called and moved to a task below, right here. This other part that you see, the syncer is completely inactive for reg test, except it just commits the reg test genesis token. This is because the reg test goes through submit block for followers.
You lost sound again.
Lost sound again. This is because, where did you lose me?
You were talking about it being inactive for reg test.
It's inactive for reg test because reg test only adds new blocks to the chain via the submit block method. And we'll see that shortly as well. But first, let's take a look at the sync component. So the first thing sync does is it requests genesis. This method will check if the state already contains the genesis hash, and if it doesn't, then it'll get it. But otherwise, it will just return immediately. And it doesn't sync any blocks until after the genesis block is committed. So that is unusual. Every other block can be synced and handled in parallel, but the genesis block, we request it once, and we handle the block response, and we wait for the state to have committed it before we start trying to sync anything else. The rest of what's interesting in this is in try to sync. Whenever there's an error, it'll cancel all the downloads, wait for a sync restart delay of 65 seconds, and then try to sync again. But what this does is it looks for, it creates block locator requests, and then it gets block headers, and it downloads those blocks in try to sync once. So it obtains the tips. Oh, it just does this first, which is fine, because it's in a loop. So first it checks if there's anything that's already done in downloads or in flight, and if it is, it'll try to handle those responses. And then once it's done with everything that's already in downloads, it will go over to try to request more blocks based on the tips that it obtained via the block locator requests. And then once it's got no more extra hashes, it'll try to extend the tips further and then continue doing the same thing. Requesting blocks, requesting blocks just queues them for downloading and verification. And then it will go through whatever's downloaded already. Once it's processed all of those, it'll request more blocks and so on until it reaches the chain tip. And that's most of what's interesting here.
I have the answer to parallelism for Halo 2 verification. So when you do a batch verification, there's some parallelism there, but within the verification of a single proof, there is no parallelism in the Halo2 library.
Okay. So we probably want to increase that limit.
Yes.
Thank you for looking into that. We will do that shortly. Okay, so
if anyone wants to verify that, it's in source/plonk/verify.rs and source/transcript.rs.
okay. So after the syncer, we have the mempool. The mempool has this transaction sender and receiver. All it does is send new transactions that have been added to the verified set of the mempool to this, and then there's another task that will gossip those to the peer set. It starts with a state of none, so the mempool is inactive when Zebra starts up at first. There is a debug enable at height, and if you set that to 0, once the state is committed to the Genesis block, the first time the mempool is polled, it'll activate the mempool. So that's how that works.
Why is that called debug enable at height?
Because usually the mempool is not going to be active until the sync status is close to the data. And that usually works, but sometimes in tests or when debugging things, we want to activate it at a lower height. So for example, when we had the issue with testnet, we need the mempool.
Oh, I see.
Mm-hmm. But it was estimating that it was close to the tip at all incorrectly.
Right.
So we had to use that field.
Got it.
So a lot of what's interesting in the mempool is actually happening in the poll ready function method, which is also it's a little unusual for Zebra, but the first thing it does, it checks the last tip change. This just borrows the latest chain tip block, gets the tip action. The tip action is based on the last change hash as well. So if it's not equal to the last change hash, we assume that it's a reset. And in this method, we also check that it's not a network upgrade activation height, because all of the network upgrades are also treated like resets. And then we update the state with the tip action. Included on self is the sync status, so it checks that it's close to the tip or that it's enabled by debug. And then if it should be enabled, it will create a new active state, most notably the storage and the downloads, which can be used to start adding transactions to the verified set. If it's not enabled, it just returns right there. If it is enabled, we start handling the tip actions. So for the resets, it'll take the entire active state, drop it, and put in a new state. But before it does that, it'll get all the transactions that need to be retried. And once it's created the new state, it will try downloading all of those transactions. If they're gone, they're not going to be gone because these, oh wait, yeah, no, they're not going to be gone because this will return the full transaction data. And it will essentially just verify them. We'll take a look at this in a second, but first let's just get through the poll ready method. If the active state is enabled and it's not a tip action reset, we create this new hash set of send to peer IDs. This is what's going to be gossips to the rest of the peers once we've gone through whatever has been, like whatever we can add to the mempool. So the transaction downloads is somewhat misleadingly named because it also verifies the transactions. We know that all of these results, if they're okay, they've been downloaded and they've also been verified by the transaction verifier, but we don't know necessarily what tip height they were sent in to verify with. So this is the expected tip height. We have the best tip from the latest chain tip. If it's equal, we'll try inserting it, and there's just a couple of validation rules here. No, I think it's mostly just duplicate spends, and if the verified set already contains it, or if it's already been rejected. So if there's a rejection error, then it'll return that. Otherwise, it just inserts it and it says if it's okay, add it to it's one of the transactions that we want to gossip to our peers. So it's added to the send to peer IDs set. If it is not at the expected height, we need to re-verify the transaction with the new height. This isn't very efficient, but it's also relatively rare because transaction verifying happens pretty quickly, and the tip only changes on average once every 75 seconds. If this is an error, it will reject it if it's needed. It depends on what kind of error it is. Sometimes it's just a cancellation, in which case there's no need to reject it. But sometimes it's invalid, and we do need to reject it because we don't want to try re-verifying the transaction again. And if it's elapsed, it'll just say, like if the transaction verification request is just timed out, it'll just log a message because there's a good chance that it was. Actually, I don't know what would happen here because it's only the block requests to transaction verifier that are going to await the UTXO. So we really don't expect this to happen. This maybe should even be a warn. But this is how.
So you said earlier that when transactions move from the mempool to the mined block, if you've already verified them, then you don't need to verify them again. So do you keep track of whether you must keep track of whether the mempool transactions are being verified. So there could be a case where you haven't verified it yet and you have to wait for it to be verified before you consider the block to be valid. Is that right?
So currently, all transactions in blocks are fully verified, and the transaction verifier doesn't call the mempool at all. It doesn't even have a handle to the mempool. But there is a PR.
Sorry,
yes.
I thought you said earlier that because you assumed that transactions in the mempool had been verified relative to the best chain tip, that they didn't need to be verified again when they went into a block.
That is correct. It's one of the performance optimizations that we actually had an issue for because it's a relatively big one. That said, it's only being fixed now. There's a PR open for it. This is what the PR is doing. It just there's a new there's a new request type in the mempool. They'll get it with all its dependencies because this is based off of the transaction verification. And if it has all those dependencies, it doesn't check the order.
Your sound is gone.
Oh, and if it has all the dependencies, it doesn't check the order. It just lets the state handle that, and it says this transaction is probably valid. It's already been validated for the mempool. But that's still a PR.
Oh, I see. Yeah, I see. Yeah, I see how the PR works. So you still validate all of the transactions for the mined block, but there's a shortcut in the case that it's already been validated.
Yes.
Got
it. So here, if it's inserted into the mempool, we add it to the send to the peer IDs. Later, if it's expired, because the tip height has changed, it's going to be removed from the send to peer IDs. If the tip action is a grow, so if the best change just grew by 1 block, then it's going to get all of the mined transactions from that block and remove them from the mempool and reject them so that they can't be submitted again. It will cancel any verification attempts for those mined IDs in case it was gossiped to Zebra a little bit late or Zebra downloaded it a little bit late. And we clear the tip rejections because I believe this is just chain effects. Oh no, it's both. We clear the tip rejections because transactions that were invalid based on the best chain one block prior could become valid now. We remove the expired transactions from the peer list, and if the send to peer IDs is not empty, we'll send that to the transaction sender here. Now, before we look at where these transactions that are supposed to be gossiped are being received in the gossip task, let's just quickly look at how transactions are queued. So this is the mempool request for queuing a transaction to be added to the verified set, to be verified and added to the verified set. It does a very, very quick check here first. If it should download it. All this does is check that we don't already have the transaction in the mempool and that we haven't already rejected the exact transaction ID from the mempool with the same auth digest and not based on the chain effects, but based on that particular transaction. So if that passes, we will queue it to be downloaded if needed and verified. This is where we get the expected tip height just before we send it to the transaction verifier here. And then if it's a gossips transaction, actually this should probably happen a little bit later for transactions that are only IDs. But if it's a gossip transaction with just an ID, it will try downloading the transaction first. And if that succeeds, it moves on to the next step. Or if it already has a full transaction, it will move on to the next step, which is to send a transaction request for a mempool transaction with the next expected block height and the transaction as it is. It will map that into a mempool transaction if it's okay. Once that comes back to us, we will...
Just a question first.
Yes.
So there are basically two kinds of transaction ID. There's the WGX ID and the TX ID, depending on it's specified in tip 239.
Yes.
So that code there is handling either case. Is that right?
Do you mean this? Hold on, let me. Do you mean the quick checks that we do before trying to download the?
Let me check in zip 239 because there's something that is niggling at me there.
Okay.
Carry on in the meantime.
It does check the auth digest when seeing if a transaction was already rejected. So if a transaction with the same mind ID has a different auth digest, it could be correct now. So it will try to verify that again.
Right. It's that there are two inf types, message to TX and message TX.
Oh, you mean the gossip IDs? It could be two invite. Wait, for V5 transactions?
No. This is for in general. It's so V5 should always use message WTX and V4 should always use message TX.
Got it. So for V4 transactions, we do always use the quote unquote legacy unmined transaction ID, which is just the mined ID.
Right, yeah.
For the new ones, we use both the ID and the auth digest.
Okay, perfect. Thanks.
Okay, so we try downloading it here, or we already have it here, and then we pass it to the transaction verifier. If that's okay, then we map it to the transaction and the tip height. Well, sorry, we just do a metrics count here. If it's an error, we map the error, we just ignore the error and just keep the transaction ID. We may want to change this in the future to return a little bit more information, but then we wait on either the cancel receiver, which this method will return a cancel sender. So if the transaction, if the mempool for any reason wants to cancel the transaction, it will be selected first, and this will just be dropped. Otherwise, if the verification completes, then we will send the results to the response channel. this is actually incorrect. There is another PR open right now for moving this into the mempool so that it only sends an OK response after it's been successfully inserted into the verified set. But for the most part, if there's a transaction verification failure, then this will send an error to the caller. For example, send raw transaction. Once we have built this entire feature, this entire Tokyo task, we will insert it into the set of pending downloads and verifications. And we will insert the cancel sender into the set of cancel handles. It's not returned.
You lost some there. I was going to say also, I said something incorrect, and since this is being recorded, I better correct myself. It is not required to use message TX for V4 transactions. You can use message WTX for either, but the message TX is shorter. So you probably want to continue what you're doing. It's just I said something that was technically incorrect.
Got it.
Carry on.
Okay. So yeah, it's just it inserts the cancel handle here, but the important part is it pushes the task into pending, and then going back to the poll ready. That is where these results come from. So it polls next, and poll next will take a look at the what? Oh, this is wrong. Going back here. Yeah. The implementation of stream for downloads, which is the actual poll next method that was being called there. It'll remove the cancel handle, and if the join result is ready, it'll remove the cancel handle and return the verified transaction or the unverified transaction so that it can be added or rejected in the mempool here. And that is most of what's happening in the mempool. The rest of it is just responding to requests about information. For example, transaction IDs when a peer is asking for the inventory that Zebra has, or actually trying to download the transactions. Full transaction is used by the get block template method when building block templates. And check for verified transaction it doesn't actually do anything, but because of Tower Buffer expecting a call to the underlying service right after a poll ready, in order to keep calling poll ready and not get any unexpected behavior from the Tower Buffer layer, we need to pass some sort of call in. So this is just a no op. And then if the active state is disabled, it'll respond with an error or with an empty response to every request. And I think that's about it for the mempool. Are there any questions about this so far? Okay. So
okay, did you cover the dropping transactions when the mempool gets full with the zip401?
Oh, when it gets full. You're right, actually. Thank you for reminding me of that. So when the transaction is verified successfully and the expected tip height is still the current tip height, it'll try inserting it here. It checks one more time that there's no rejection errors in between when it was initially queued and when it was finally finished verifying. If there is, it'll return the error. It checks that the verified state still doesn't contain the transaction ID, and then it'll try inserting the transaction. If the transaction is in the rejection list of the verified set, it'll just return the So if the transaction has a span conflict with another transaction in the mempool, those aren't checked by the transaction verifier, so we check it here. This is the main check that happens in the mempool before inserting. The rest are mostly just checking that the total cost is still okay and that there aren't any rejection errors, and then it's not like a duplicate itself. So if it's an error, if there's a rejection error in the verified, the storage will also return the rejection. And I think, Daira-Emma, what you were asking about was the total cost.
Yes, absolutely.
Okay, so there is a configured cost limit that you can define in Zebra's configuration. And if the verified sets total cost, and I think this, okay, well, it's updated here. And this is just size, I believe. Yeah. So if the total cost is greater after inserting the transaction than the cost.
It's a bit more complicated than size. Or is this the same in ZBD as in Zcash D? Because Zcash D doesn't just use size as a there's a penalty if it's less than the conventional fee.
Yes. Yes. Oh wait, sorry. So if it's less than the conventional fee currently in Zebra.
Sorry, there's two things. There's eviction weight and cost, and eviction weight takes into account the conventional fee and cost doesn't. Yeah, you've implemented it correctly. That's fine.
Okay. So yeah, it just checks that the total cost of the verified set is still below the cost limit. And if it's not below the cost limit, it'll randomly evict one transaction as is specified. And if that randomly chosen transaction happened to be the one that we just inserted, it will update the result to be an error at the last second. So I think that's everything now.
Yeah. Yeah.
It's a little bit more complicated than the PR for transaction dependencies, where evict1 will also remove any transactions that are dependent on the transaction that was randomly chosen to be evicted. But that's the general principle.
Yeah, thanks.
So I think the next component is the RPC server. And here we're using.
So before you go on, did you say that there was that hadn't been implemented and there was a PR, or that it had been implemented?
Verifying transactions. Yeah, that's there's a PR open for that as well. It's gotten one review.
Oh, I see.
Second.
Sorry, was that eviction logic in storage.rs?
Oh yes.
Oh, okay, thanks. I was wondering if it was a loop or an if statement.
No, it's a loop.
Okay, thanks.
Yeah.
Yeah, that's what for a one specifies. You just keep evicting until you're below the cost.
Yeah. Okay. Good.
So next we have the RPC service. There's nothing terribly interesting here. It just assigns all of the fields that are required to the. There are two interfaces or implementations for RPC. There's the get block template RPC, which is behind a feature. We may be removing that feature soon because it's a pretty necessary feature. And it's not experimental anymore. And then there's the regular RPC impl. This has all of the older methods. This has most of the newer methods. And the RPC server can use multiple threads. By default, it uses as many threads as are available on your computer. And there is just a little bit of middleware that will replace, I believe, 2.0 request JSON RPC 2.0 requests with 1.0 requests for compatibility. Nothing terribly interesting here, except that it just returns a server instance and handles so that when Zebra is shutting down, it can tell the RPC server to shut down, and it can, if the RPC server task panics, force a shutdown of the rest of Zebra because something has gone horribly wrong. So that's about it there. If the RPC server is not enabled in the configuration, it'll just return pending features that do nothing, so that the Rust compiler is happy with the types. The actual methods are in these two files. So the interfaces are described here. This is the set of methods that are always available in Zebra. And these are also available by default because the get block template feature is a default feature. But anyways, so yeah, we have the get block info, get address balance, and so on. Let's just look at a method, for example. So we have these async moves. This just is a synchronous method that's going to return a future for the JSON RPC scheduler to run and then respond to the request. It doesn't have to be a future, but because we're using futures throughout most of these methods to interact with the state service, for example, most of these methods are returning an async block. Before we start creating the future, we do clone everything. These are, again, just arcs because the state is a buffer layer with a channel. So there's very little cost to cloning these. The network as well as an arc because there's actually some data there now. There's testnet parameters sometimes. And we make a few requests. For example, this one is get blockchain info. We get the block header of the tip, and we use that to return like not the hash, but the value pools for, oh, wait, no. Yeah, I guess no, I'm not sure actually what the header is used for here. Maybe the height. But that's just an example of a method. This transaction might also be interesting. This is where the mempool request queue is used, and the one-shot receiver that it returns is awaited on for an error before a response is sent to this request. We have this cute little trait that just maps the server errors, that maps all of our service errors to JSON RPC errors. Conveniently, nothing else really interesting here. The get block template method is the one that's super interesting in this file. So let's just take a quick look at that. Oh. We're cloning a lot of things here. So we check the sync status before we return a block template. We check if the request was supposed to be a block proposal, and we return early if it was. With this is also a future, but it's just in its own little function. We check that the parameters are valid. So if the mode is template, then the data should be none. And if the mode is proposal, then the data should be some. Simple things like that. We check for a poll ID, and if there is one, we will wait until responding for the poll ID to change. We check that it's synced to the tip. We check that we have a miner address to include into the template. We get the relevant information from the state about the best chain tip, like valid block times. And then we get all the mempool transactions. So this is where the full transactions request is used. In fact, that's almost all this is doing, is just sending that off and checking that the chain tip hash is still the last seen mempool tip hash. For long poll requests, we create a new long poll input with the mempool transactions and the key information from the state. We check if the max time has been reached and always return it. Otherwise, we will wait until this is a loop, so we will wait until the long poll ID has changed from the one that was passed in. And before we go into the next iteration of the loop, we will wait either a short time for the mempool request or for the best chain tip to change. And if the mempool requests, if the mempool transactions have changed to the mempool, will still be true because the old template is still valid. And then we have the 317 transaction selection, which just randomly selects.
Go back to yeah, go back to the last file and scroll up a bit. There was something about the a difference on testnet. A bit further. Yeah,
Oh.
that one. What do you mean by the max time changes the block difficulty?
So you know how on testnet there's that rule that I think after 90 minutes the block difficulty is reduced significantly?
Oh, yes. Okay. So
That's all it's saying.
oh, right. Okay. Yeah, got it. Carry on.
We mark the best chain tip as seen. This is just a local receiver, but we don't want to process that multiple times. And then the only other interesting things here are selecting the mempool transaction based on ZIP 317, which is the recommended algorithm, randomly selecting those with conventional fees, and then randomly selecting those with less than conventional fees, although the unpaid action limit is currently 0, so it really only accepts the conventional fee transactions. And then we have the get block template constructor, which will sort all the mempool transactions as is done in Zcash D, and otherwise it just generates the Coinbase, calculates the new roots based on all the transactions that are going to be included in the templates, converts some of these types into the types that are going to be included as fields on the final structure and the final response, and then passes this back.
There was a comment there about Zcash D, about it sometimes sorting and sometimes not.
Oh, yes, this is
kind of
configurable.
weird.
This is configurable. Why is it weird?
That Zcash D only sometimes seems to sort.
Oh,
Is there an issue against Zcash D for that?
I don't believe so. I
Okay.
don't remember it being mentioned in the PRs where this got decided. That's strange. It's never happened in my experience, though.
Yeah, I think it's supposed to sort, but anyway. Yeah.
I thought you were saying like sometimes Zebra doesn't sort it, which is true.
No.
So yeah, that's pretty much it for this method. Submit block. I'm also going to show off this one because I think it's really nice. I think Zcash does the same thing, but when you submit a block through the submit block RPC, it just goes through the exact same process that blocks that are downloaded from peers go through. It gets submitted to the block verifier. That's all. It doesn't really do anything else. It's very, very simple, and we know that it's correct because that's what we use for syncing blocks normally. I think we're almost done. Let's see what else is left. The indexer RPC server, it's very similar. It just has its own methods. Currently, it's only the chain tip change method. This is here instead of in the JSON RPC because it's stateful. It uses HTTP2 and push server sent messages or events to the client when the chain tip changes. It doesn't actually send any information about the chain tip change, but that's not important because it's only to notify the client so that the client can pull the RPC server for it can just get the block. And we haven't looked at the tasks yet. So this is also that's not what I wanted. This is a very, very simple little task that just waits for a chain tip change. And if it's close to the tip, it will randomly select a few. Oh, we didn't do the peer set either. Let's do that next. But if it's close to the tip, it will randomly select, I think 2 or 3 peers to gossip the block ID to block hash to. And there's a bit of a delay. This was a little problematic during the testnet issue, and it still, I think, needs an update. Yeah, it still needs an update. But usually it works when the network is stealthy. And then there is the queue checker. This is the one that just repeatedly polls the mempool so that the poll ready function is being called, and it will gossip new transaction. Well, it'll send new transactions to the transaction sender, to the transaction channel, so that they can be gossiped. And then there is the task that actually does do the gossiping, which takes the mempool transaction receiver that's returned when we're creating a new mempool, and where the send to peer IDs sets are sent, waits to receive an item, and does the same thing as the block gossip task. It just sends it to 2 or 3 random peers. And I think that's it for. Oh no, there's a little bit more. I'm not going to go into this one, but all it does is update the CLI. So if you've used Zebra with the progress bars feature, you see, I think, 5 or 10 progress bars in your console, and all the regular logs go into a file. This is the task that's responsible for updating those bars. The end of support task is Zebra expires after 16 weeks, usually, if there isn't a network upgrade coming up that is not deployed yet in that version of Zebra. This just handles that, and it panics when it reaches the block height that's is the last supported block height for that version of Zebra. And then there is the mempool crawler task, which will just crawl the network for new transactions in other peer nodes mempools, and try to add them to this node's mempool. What else? We've already looked at the sinker task. The miner task is interesting. I think that's the last thing before the peer set. I think I'm going to show this first. So all this does is there's a task for calling the getBlockTemplate method. I'm not sure if it uses long polling. I don't think it does, because we actually have the latest change of channel here. And it pushes those to another watch channel, and it starts up a bunch of mining solver tasks that will try to mine the solution and the block hash for a block template. And if they have found a valid solution and a block hash that is below the difficulty threshold, it will attempt to submit the block. So it marks the local copy of the template receiver as having been seen, so it doesn't try to receive it twice. It also has a cancel receiver, and most of the work is done in mine block above right here, where it will modify the header nonce a little bit by the solver ID, spacing them out evenly between the entire space that the nonce can occupy. So if there are 16 threads and the nonce is 32 bytes, then it will go forward by increments of about 16,000, 2 to the 16. And then each solver thread will independently update its nonce by 1 and try to hash that, see if it finds it under the difficulty limit. Solution solve is using the Aquahash trump solver that is open in Zcash. This is currently actually not doing much at all, because we can't publish with crate that is only on GitHub. The Aquahash crate also has to be published for those changes in order for us to publish a version of Zebra that uses it. But there's also a branch open for that is using the tromp solver branch in Zcash and can actually solve the Aquahash solutions on testnet.
I'll have a look at whether we can get an Aquahash release up.
Thank you. So then once the blocks are actually mined, I think it checks the solution one more time here. No, it doesn't. Okay. Once the blocks are actually mined, then it will try to submit those blocks via the submit block RPC. And that's about it for the miner. I think the final piece is just double check that there's nothing else here. So the final piece is going to be the peer set. And that is being created here. So when we create the peer set, first we need a handshake builder. The handshake is what actually creates the client structs. And the client structs are responsible for receiving messages from peers over the network and responding to them by relaying those requests over to the inbound service. And they're also responsible for, of course, doing the initial handshake. There is a peer set channel. This is used to add new peers to the peer set. So I think just below, so this is the add initial peers function. It will take the peers that are in the configuration or in the and it'll try to connect all of them up to a connection limit, and it sends them to this channel, the peer set channel, and the peer set channel is received in we'll see that in a second. There's also the demand channel. The demand channel just says we need more peers. This is an empty struct. It's just a signal. So if there's a request coming from the syncer, for example, and there are no ready peers to relay that request to, then instead of sending it to a peer, it will send a more peers message to this demand channel. And then there's another function here and another task that will perceive that and attempt to pick some candidate peer addresses from the address book and try connecting to them. And then once they've completed the handshake, those will go into the peer set channel. The peer set channel, and then the peer set will try adding those into its set of peers. A little confusing, I know, I'm sorry. We also have this task for accepting inbound connections. It also uses the peer sets channel to convey those over to the actual peer set. And we have the candidate set of outgoing peers that we want to connect to in response to load. We also have a count of active outbound connections. Okay, so let's look at initial peers, accept inbound connections, and there's one more down here. Crawl and dial. Starting with at initial peers. I guess this from the config, the set of initial peers, goes through them all, attempts to do a handshake with the outbound connector. And then if the result is okay, it will send those up. If not, it will just complain in the logs and go over to the next one. Accept inbound connection is just listening on the relevant port. And if there are any requests for a handshake, it will pass that off to the, it'll just, hold on, let me read this. It'll accept the connection. It will track the connection and active inbound connections. And then here is where it will call the handshaker to create the new client. And then it will, if the handshake task is successful in send off to the peer channel. what else is there here? We also need to look at the handshaker, but before we do that, a crawl and dial. So there are a few crawler actions, demands, demand handshake, timer crawl. So on a regular interval, it'll also crawl the network or it'll also try to add a peer. It takes the demands channel and it waits for either the timer or some handshake to have completed or for a new demand signal. And if there is a demand signal or a demand handshake in crawl, it will try getting a candidate's address from the candidate and just dialing it. And dialing it, we also use the handshaker.
I'm losing a lot of audio now.
Losing a lot of audio. Is this a little better?
Oh yeah,
okay.
Yeah, that sounds better.
Awesome. Nice. Okay, crawl. Nope. I was looking at crawl and dial. Here. Okay. So it tells it if there's a demand signal, or if there's a timer, it does the same thing, except instead of going through no, it does the same thing. It just crawls first, and sees if it can send out get address requests or get adder requests to its peers to update the address book first, and then it dials. And those are the two main things here. The other ones kind of just log, unless there's an error, in which case it fails. I mean, the task just stops. But that's for fatal errors. I think next is the handshake. And okay, so this is the outbound connector that we saw in a couple of in crawl and dial and in all of the things that connect to appear and create a new client. We call it with a handshake request that includes the listener, or yeah, and then we get the nonce. We clone the inbound service because we're going to need it for the client. Again, this is just a pointer, so it's very cheap to clone. We get the address book updater and all of the other things that the client is going to need, or the handshake is going to need, like the minimum peer version. We negotiate the version. So this is the network protocol version. We create a new codec for the network. We update the address book with the address of the peer we're connecting to, so that if Zebra restarts or if it loses the connection, it can try reconnecting to it later. It will try reconfiguring the version of the codec to match the negotiated version, because sometimes peers can have a lower version than Zebra, a lower network protocol version than Zebra, and will still work correctly. And it has a server TX and server RX. I thought this was client TX and client RX elsewhere, but this is just where the requests and responses from up here come. And a bunch of other stuff that is used for handling the client messages. We will see these later when we're looking at the clients. This is the task, I believe, that actually handles those messages, if it has, or not. What does this do? Oh, this is the ping pong, I guess. That's the heartbeat. So this is the task that does the heartbeats, and this is included in the client, and it's checked every time the client is sending off a request in the poll ready method. It gets the remote canonical address and includes that in, I believe, the connection info. It adds it into the address book as a new cost address. and then it creates a new connection. And the new connection is where most of the interesting things happen. So this one. Yes, I think it's this one. So if it's a waiting request, it will wait between the PRs. One of these is for sending things, and one of them is for receiving messages. And we will figure out which one here. So the first one is for receiving messages from the peer, and it'll handle the message as a request first if there has been no request to request something from them. If a message was sent to the peer to request some information, then it will change the state of the connection so that Zebra is expecting a response from them, and then it'll handle this differently. But not here, it's the outer match statement. So this is what happens if we're just awaiting a request and handle it that way. If we're awaiting a response, it will do the opposite of the select statement above, where is there an if here? Okay. This is the handler is finished. Sorry, that's not the correct one. If we're quitting a response and the handler is not finished, then it will wait for a cancellation. It will start reading the message and decoding it, and it will process it as a response. If it's an unused message, then it will try handling it as a request anyway. So if the peer sends a response for the wrong request, essentially, or if it's not the response for the right request, then it'll try a request as well. And
so is the state machine always in a either request or response state? Because I that's not how Zcash works. I think.
I believe it is.
So I think Zcash will. Actually, I can't remember, but I think it sort of synchronously or well, it's using locks, but we'll calculate the response in most cases and then queue it on the outgoing message queue. So it's not an explicit state machine. It's more it's written as sequential code.
I see. Yeah, that's not a state machine. It's either awaiting a request or awaiting a response. So if it hasn't sent a request to the peer, it'll always be awaiting a request, and any message sent from the peer is treated as if it's a request.
So what happens if you never get a response to a particular request?
It times out. I think it times out.
Okay.
Yeah, and
and will you ever request more than one thing in parallel?
From one peer? No.
Right. Okay, that makes sense. Yeah. So I think that's ends up being pretty much equivalent to what Zcash does. It's just implemented in a different way.
The rest of this is just handling particular requests and routing them over to the inbound service.
There was one other thing I wanted to ask. So you've made a request, you're awaiting a response, but the peer node sends a request instead. When you've handled that request from the peer, do you stay in the awaiting response state, or do you cancel the request?
That's a good question. I mean. Let's look at that now. So we'll replace it with finished. it looks like it'll update the state, and it'll say that it's awaiting a request again, and it will fail.
Oh, it fails the original message, but hang on though. That will cause spurious failures because so how are ping and pong messages handled? Because you might get a ping or a pong at any time independently of other messages, right?
I think even the ping and pong seems to just return the response nil. Like
I see.
any message that
So
is received is considered a response. And if it's not a response, then it's considered a no response, and Zebra ignores the response, as far as I can tell right now.
I'll make a note to have a look at this.
Thank you.
That's it.
Yeah, I'll look into it a little bit later, and I'll post on Discord or update the comment.
Yeah, this
if I'm wrong.
This is too complicated to handle on this call.
Yeah. Then the other component in Zebra Network that I know to look at right now is the address book. So let's take a quick look at that too. So we saw the address book.
Oh yeah, so there was something I wanted to ask related to that. There was an attack on Bitcoin, basically based on BGP hijacking, and Bitcoin Core made a bunch of changes in response that I haven't really had a chance to look at in detail. But does ZebraD have those fixes from Bitcoin Core, or equivalent ones?
Was the issue that the getter response was returning far too many addresses so that the entire address book could be revealed very quickly?
So there were several issues. The one that I'm thinking about is this paper that I've just posted into the chat. It's called, so for the recording, it's called Hijacking Bitcoin Routing Attacks on Cryptocurrencies.
Is that a kind of attack that could be solved if we had like network public keys and network layer cryptography?
I'm not sure because it's basically, so the response to this was to make sure that you had a sufficiently diverse set of addresses and different AS prefixes. So does ZebraD do anything like that?
So Zebra will, I believe, regularly try to get addresses for candidate peers from all of its current peers, or from one of its random current peers. The requests are, like, the requests to the peer set are also routed to a random peer in the candidate in the peer set. But I'm not sure if that's enough to make that attack feasible. I'll need to look into it in more detail later. I'll do that.
I mean, it was just a heuristic improvement. It wasn't giving you any guarantees or anything. Just making it more difficult so that you had to hijack more BGP servers, presumably.
Okay, could you send me a link to the PR where it was fixed, and I'll take a look at that later, and then I'll give you a more accurate answer there.
Okay, yeah, the Concord PR, yeah. I will have to go soon, actually.
Okay, we're almost at the end here. I was going to show the address book, but that's not terribly interesting relative to the peer set. So let me just quickly show off the peer set. This is the demand signal where we can send a request for more peers so that the crawl and dial task will try to connect to another candidate with the outbound connector. This is the set of ready services. So all of the connections that are awaiting a request and can be, we can send a request to them, not all will be awaiting a response. This is the set of unready services where we are awaiting a response. And let's just go to the call method now. Wait, I was there. Okay. So first, there's just the poll ready. So it'll check the poll discover. The poll discover is the peer set channel where we add any new connections. This is going to check. This is going to try to receive any of those new connections if there are any. We poll for background errors, like if there are heartbeat, if it's an issue with the heartbeat, or if a connection has been dropped for any other reason. We poll our inventory. I think this is another service. I'm not actually entirely sure what this does, so I'm going to skip it. And then we poll unready to see if any of them can be, we already got a response from any of them and can add them back into the ready services. We disconnect from outdated peers. We check for errors, and then I thought we select something randomly, but no, I guess we do that here. And then for most of these requests, we will route the request to P2C, which will take a ready service at random. Call stack is long. It just takes a peer at random, and it takes the request. For the advertising transaction IDs or blocks, so these are the requests used by the block gossip and mempool transaction gossip tasks. These will broadcast it to, and we're about 3 peers is the answer. As long as we have 3 peers that are ready to receive a request. And route in, I'm not sure what these do yet. So I think that's about it. The last thing would be the address book. It doesn't do anything particularly interesting. It just has a channel, I think. Oh, no, it doesn't have a channel. It's updated with a new text.
Oh, that's unusual for Zebra.
It's very unusual for Zebra, yeah. So we're always very careful when we're touching the address book because we don't want to lock out of that time. So there's very few places where it's actually locked. One of the only ones is in our PC method for get peer info, but I don't know where it is right now. But there's another task that receives items from the address book updater channel, and it will try inserting them into the address book. It just locks it, mutates it, and unlocks it after the message. And I think that's about it for the walkthrough. Thank you all for joining. If there are any final questions, now is the time to ask.
That was great. Thank you.
Yeah, thank you very much. That's amazing.
Thank you for bearing with me.
I will try to remember as much of it as I can.
Oh, can rewatch it.
Yeah, my brain is pretty full.
Yeah. I hope the sound is okay on the video. It might be a little bit difficult. Anyway.
I hope so too. I'm sorry about that.
No, it's okay. Most of it was understandable.
I don't have a question about any of the software contents here, but I did have a desire to have like another walkthrough that's just about CI, like, and also testing. Like, here's how we run tests. Here's how we build packages, do benchmarks, anything else like that. I would like to learn about.
Sure. So there are different kinds of tests. A lot of the unit tests are going to be in, like, for example, let's just look at something randomly here. And if we can do, wait, what? Test dash dash release dash dash lib dash p and the name of the package that we're testing so that it only runs those tests. We usually use release because there's so many tests that it's a lot faster. The unit tests are very easy to run. There are also a set of acceptance tests. Many of them will also run by default if you just run cargo test dash dash release. Which will run the test for every single crate, but there are some of them that are ignored, or many of them that are ignored. Oh, it's ignored now. For example, sync large checkpoints mainnet, and some of these rely on a cached state. Some of them also rely on like while the instance running while the test is running. Or at least having binary available for Zebra to run. Many of these, there's instructions in the module documentation for the acceptance test to like on how to run them. I think almost all of them except for maybe 3. And those 3 are really trivial tests that you usually don't want to run anyway, but we do want to have in CI. So for example, if you want to run the like all gRPC tests, you can just run this, but you need a few environment variables for the path to the cache state, like loyalty, data directory. We also have a couple of tests for generating checkpoints. This doubles as also like generating the checkpoints that we can use to update the checkpoints that we deploy with the release of Zebra. Another thing I want to show here is the test type. So we have a bunch of utility code for starting up a test child and using either any state. These are for the stateful tests largely, using either any state, using the RPC server, stuff like that. And if we look at an example for the submit block test, this is using a cached state with RPC. It checks that it can spawn it for the test type, which right now just means the environment variable for skipping network tests is not set. It gets some raw future blocks and it does its thing, but Zebra D here is a child process that it's actually running the entire Zebra D child process and interacting with it from the test by RPC methods. It also checks the logs that it's outputting, but that's how a lot of the acceptance tests work. It runs it in a box in another child process and tries to monitor how it's going. There are some exceptions. Actually, there are a lot of exceptions in the acceptance tests. For example, this one, where it just starts the block verifier and the RPC methods independently, and it calls them directly in one process. Another thing I wanted to show here. Nothing I want to show here.
I have to drop. Bye, everyone.
Okay. Bye, Daira-Emma. I can't remember it.
A follow-up question: is there a document? So one thing I'm curious about is there like is there a way I can say run all tests that don't require external dependencies as a prerequisite versus not, such as like there's a policy that anything that requires an external dependency has to be ignored, or anything like that, or a document describing those different cases? Okay.
I don't think so.
Got it.
Sorry.
Yeah, no, that's fine. Okay, thanks so much for the overview.
Yeah, no problem. Thank you for joining and listening. This is bugging me. I forgot something. Oh well. It's been a very long call. I think we should end it here.
Yeah.
Nate, I will get the answer to what the other thing I wanted to mention was, and I'll post it on Discord so everyone can see. Yeah, thanks for joining, everyone.